Welcome back, Physical Science 20. In this section of PW1, we look at sound waves. So we've looked at waves in strings, springs. We talked a little bit about waves in water, two-dimensional medium, and sound is considered to be a three-dimensional medium. Okay, so just quickly going through here, sound is an important part of existence of many living things. For humans, the sound of a siren can heighten our awareness of our surroundings, while the sound of music can relax us. You already are familiar with some characteristics of sounds, including sound volume, and you may be familiar with tone and pitch from your everyday experience or from taking music. Without thinking about it, you can use these and other characteristics to categorize many of the sounds that you hear. For example, some sound patterns are characteristic of speech, while others are characteristic of a musical group. In this chapter, you will study the physical principles of sound, which is a type of wave. You will also use your knowledge of waves to describe some of sound's properties and interactions. So, sound, pressure variations. Over here in the notes here, it says, put your fingers against your throat as you hum or speak, and you can feel vibrations. The figure below shows a vibrating bell that can represent your vocal cords, a loudspeaker, or any other sound source. And you can see as it moves back and forth, the edge of the bell strikes the particles in the air. When the edge moves forward, air particles are driven forward. That is, the air particles bounce off the bell with greater velocity than they would if the bell were not moving. When the edge moves backward, the particles bounce back with lower velocity. So if you look here, a bell that has not been struck, basically nothing. But once it's struck, it vibrates back and forth. And in class, I'll show you a demonstration with a tuning fork and a strobe light, which kind of slows down, or it appears like it's slowing down the motion of a tuning fork. And you can see it vibrated like that, making compressions and expansions or rarefactions. And of course, the difference between compressions or the difference between rarefactions is in fact wavelength. So it's the moving particles that vibrate our eardrum, which we perceive as sound. So if we take a look here, it's very similar to what we did with the spring in class. Compression, and the compression moves all the way down to the end of the spring. Tuning fork, as I mentioned, I'll show that. For simplicity, quite often we view it as a transverse wave, but of course, since pressure variations move forwards and backwards, sound is actually a longitudinal wave. The result of these velocity changes is the forward motion of the bell produces a region where air pressure is slightly higher than average. The backward motion produces a below average pressure. Collisions of the air molecules cause the pressure variations to move away from the bell in all directions. If you were to focus on one spot, you would see the value of the air pressure rise and fall. In this way, the pressure variations are transmitted through matter. So describing sound, a pressure oscillation that is transmitted through matter is a sound wave. Sound waves travel through air because a vibrating source produces regular variations or oscillations in air pressure. The air particles collide, transmitting the pressure variations away from the source of sound. The pressure of the air oscillates about the mean air pressure, as shown in figure 2 up here. The frequency of the wave is the number of oscillations in pressure each second. The wavelength is the distance between successive regions of high or low pressure, or compressions and expansions. Because the motion of the particles in air is parallel to the direction of the wave's motion, as I mentioned earlier, it's a longitudinal wave. Okay? So if we didn't have air molecules, sound would not be able to travel. So of course, space movies like Star Wars, you can hear lasers being shot through space, but technically, we would not be able to hear anything. And I have another demonstration in class that I'll do with a bell jar in which I'll suck up all the air, and we'll see how well we can hear a bell ringing with air and without air. Okay? So just like any other ways, as we've seen, the speed of sound depends upon the medium itself through which it travels. And if we're talking about air, the temperature of air actually changes the medium of air. So if we take a look here, there's a little relationship which I'll write on the next page. The speed depends on the temperature increasing by 0.6 meters per second every 1 degree increase in temperature. At room temperature, 20 degrees and sea level, the speed of sound is 343 meters per second. For the problems of this book, we'll assume that is true. So you may want to, on the next page here, just copy this out. For air, a little formula here. This is, we could use this for any speed we're looking for in air. At 0 degrees C, it's 331 meters per second. But for every increase in temperature in 1 degree, we add 0.6 on. So that T value there is how far above or below we are from 0 degrees C. Or this, sorry, this, yes, 0 degrees C. So in general, the speed of sound is greater in solids and liquids than in gases. Of course, you have experience with that. Even in class, I think I got a few people to put the slinky up to their ear and flicked it, and you can hear the sound that it makes, and it's quite different from hearing that sound in air. The table lists speeds of sounds in various mediums. So, of course, air, 331, helium, water, look at that, way quicker, 1497 compared to 331, a little more than 3 times. Seawater, copper, iron. So speed of sound travels faster in solids, liquids, definitely more than it does in gases. Sound cannot travel in a vacuum because there are no particles to collide, of course, as I mentioned. You may want to underline that. Sound waves share the general properties of other waves. For example, they reflect off hard objects, such as walls of a room, and those reflected sound waves are called echoes. The time required for an echo to return to the source of a sound can be used to find the distance, and I think we had a question dealing with that earlier. This principle is used by bats, cameras, and some ships that employ sonar. 2 sound waves can also interfere, causing dead spots at nodes where little sound can be heard. Recall that the frequency of the wavelength, the relationship lambda is equal to V over F, or V equals lambda times F, the universal wave equation. Okay, so with that and some of the demos I'm going to show you in class, we have this assignment, sound wave, speed of sound. So concepts, answer, and complete sentences. You may be able to squeeze them directly on here. What are the physical characteristics of sound waves? When timing the 100-meter run, officials at the finish line are instructed to start their stopwatches at the sight of smoke from a starter's pistol, not when they hear the sound. Why is this done? And then B, what would happen to the times for the runners if the time started when we in fact heard the sound? So of course here we're looking at comparing the speed of light to speed of sound. That table that had the speed of sound in various mediums is here. You hear the sound of the firing at a distant cannon 5 seconds after seeing the flash. How far are you from the cannon if the air temperature is that? So of course we have V equals lambda F. We also have V is equal to D divided by T. That we may have to use that, but I think this one here we can just simply use that universal wave equation. Or I guess no, in this one I think it's V equals D over T. We can use because we have the speed, we have the time, so just looking for D. If you shout across a cannon and hear an echo 3 seconds later, how wide is the canyon if the air temperature is 20 degrees C? So by knowing this, of course, we can get the speed of sound. And of course, recall that this time is to the canyon and back. So of course, you'll have to make sure that your distance and your time are consistent with one another. Sound wave has a frequency of 4,700 hertz and travels along a steel rod. If the distance between compressions is 1.1 meters, what is the speed of sound? So of course, we know what that is. Distance between compressions or distance between expansions. What does that represent? Sound emitted by bats has a wavelength of 3.5 millimeters. What is the sound's frequency in air at 20 degrees C? So of course we'll have to change this into meters. So divide that by 1,000 and that'll change it into meters, and then you'll be able to go from there. Sound with a frequency of 261.6 hertz travels through water at 25 degrees C. Find the sound's wavelength. So of course, universal wave equation. And number 8, if the wavelength of a 440 hertz sound in fresh water is 3.30 meters, what's the speed? All right. So you should be able to do those with no problem. If you have any questions, of course, please ask. And other than that, we'll see you again.